All right, we're still on section 5.6, and this is theorem 5.16 out of the book. It's on page 362. So what this is saying is if y is differentiable by t and y is greater than 0, and y prime is equal to ky for constant k, then y is equal to ce to the kt power. Now what this is saying, and what's going on here, is that y and y prime are basically the same thing. The only difference is k. K is a constant, so that's not going to change. So what that's saying is what type of equation has a derivative and the original function that are basically the same thing. And the answer there is an exponential. And we know that because we've differentiated them. In fact, e to the x, if you recall, the derivative of e to the x is e to the x. The integral of e to the x is e to the x. So the only difference is when it's not just e to the x, when there's something in front, when there's something in here with the x, it's going to vary slightly, but the derivative and the original are still going to be proportional to one another. So if you ever see something written like that, you know that you'll be able to use this formula, this setup to do that. So we're going to do example 2, which says the rate of change of y is proportional to y. The rate of change of y, this is essentially just saying the rate of change of y is like saying y prime is proportional to y. So y prime and y are proportional. So that is saying that this is holding true. As soon as that is stated, we know that we can use something that is in this form. All right. The next thing that is given to us are some initial conditions. When t equals 0, y equals 2. And when t equals 2, y equals 4. So we are given some initial values here. So as soon as we know that y prime and y are proportional, so we know it fits this model, we know that we can use this. And once we know we can use this, we can plug in these values to get two different forms of this equation. That'll allow us to solve for k, because k is the value we're missing. Well, c and k. But we're going to use them to find c and k. C and k are both constants. They need to be found. All right, let me slide this up. So we're going to first plug in these two values here. Let's use blue. So 2 equals c e to the 0, because it's k times 0. So since t is 0, it's k times 0. Now we can actually simplify this to solve for c. So 2 equals c times 1, because remember, anything to the 0 power is 1. So c is equal to 2. So now that we know the c value, we can actually go into the other set of ordered pairs. Oh my, there it goes. And we can plug in, once again, t and y, and this time we're going to solve for k. So we have 4 is equal to 2e, and we plugged in the 2 because we know this is what c is, 2e to the 2k. And we're just going to solve some steps, we're just going to solve it. So 2 is equal to e to the 2k. ln of 2 is equal to 2k, so k is equal to 1/2 ln of 2, which is going to be about equal to, once you plug it in, 0.3466 approximately. The last part of the question, because if you see here, there wasn't actually a question. I didn't write this part down, but the actual thing being asked is, what is the value of y when t equals 3? So in order to plug in 3 for t to get the y value, we need an equation. Well, we had to find the value of c and k to write our equation. We now have both of those values, so we can write that out. So our final formula is y is equal to 2e to the 0.3466t power. To find out what this would be when t is equal to 3, we simply plug in 3 for t. 2e to the 0.3466 times 3, and we will get something approximately equal to 5.657. All right. I'm just going to do this lesson kind of slowly because it's a lot, and I don't really want to overwhelm you guys. So I'm just going to do this one example and read through this, and then I'm going to give you a few questions to work on. Submit them through Mind. Thanks.